Hi, in this video we'll be taking a look at the ADCOM GFA-555 II audio power amplifier and the troubleshooting and repairs that were done to restore the amplifier's operation. Now the amplifier had two problems. One of the problems wasn't obvious at first, but became obvious during troubleshooting, and we'll get into that shortly. We'll take a quick look around the amplifier and the location of some of the components and the general layout. Now this amplifier is rated from 20 Hz to 20 kHz, 200 watts per channel into 8 ohms at 0.04% total harmonic distortion, 325 watts per channel into 4 ohms, again 0.04% total harmonic distortion, and 600 watts per channel bridged into 8 ohms at 0.09% total harmonic distortion. Very conservative ratings. The amplifier is very well built and very well designed. So looking down into the amplifier, you can see this is the right channel components: power supply, filter capacitors, bridge rectifier, the output devices, all on the right channel. On the input board, it's basically divided in the middle. You have the right channel and the left channel, some common components for some power supply on that board right here. And the left channel, again, a duplicate of the right channel. You have the two filter capacitors, rated 15,000 microfarad each. Of course, there's the two power supply rails with the common ground. The bridge rectifiers are mounted on these metal brackets, which are also a ground tie point, and this strap or bus across here is a ground point. So you would not get a shock if you were to touch this when the amplifier is operating. This is actually a ground connection, and they've used a very wide metal strap, which is a good design for the ground connection. This wire goes off to the speaker terminals, and this is over to the transformer. AC input on the side, some taps on the transformer, very large toroidal transformer with a metal cap or can over the top, so you can't actually see the windings, but the transformer is in the center. It's quite heavy, a lot of weight in that transformer. Again, on the output devices, TO3 transistors, there's 4 per power supply rail, so you have 4 transistors. Again, 4 transistors. Together you have the left channel, again over here the right channel. Some additional filtering capacitors on those boards. These are the power supply rails coming up to the output devices. The heat sinks, of course, on the back, all integral to the mounting on those transistors. So very good design, very straightforward, simple layout, but again, a good design. Not a lot of extras on the amplifier, very simple layout, but very straightforward. So I have the amplifier tipped upwards so that you can see a little better on the front panel. The power switch, the power LED lamp on the left side, distortion indicator lamp for left and right channel. It would show if the amplifier is clipping, basically being driven to its maximum output, and the thermal protection LED, and that would illuminate if the heat sinks were to get too hot and the thermal breakers would open. They'll reset automatically once the heat sinks cool. If the breaker does trip, it will turn off the bias circuit for that channel. It would protect the output devices and the circuitry. And here's a view of the rear of the amplifier. You can see the speaker terminals, the RCA jacks for the left and right inputs, a little toggle switch for the stereo or bridge mode, and the fuses. You have the main AC input fuse or line fuse, and there's a fuse for each of the power supply rails, the plus and minus rails. Those fuses are 7 amps each, and a 12 amp fuse for the AC input. So if you're following along and working on one of these amplifiers yourself, you're doing so at your own risk. These amplifiers have very high voltage in them, 82 volts on each rail, so really lethal voltages. The TO3 devices have that rail voltage on the cases of the transistors, and the capacitors in this amplifier hold a charge well after the main power switch has been turned off. There are bleeder resistors, but it takes time for them to bleed the charge down, so You know, if you were to slip, your hand touches something in here, you could get a nasty, if not lethal, shock. So again, you're working on this yourself. It's at your own risk, and you know, please be safe around anything like this where it has the high voltages that can be very, very dangerous. So if you don't know what you're doing or are unsure, please be safe and don't attempt a repair that you don't fully understand. So as I mentioned before, the amplifier had two problems. Both problems appeared to be only on the right channel. I didn't see anything initially wrong on the left channel. So on the right channel, the initial problem was that the output terminals, speaker terminals, had a continuous negative 12 volts on them. It would vary some, but it was approximately a negative 12 volts, meaning that the positive speaker terminal was actually being pulled below ground potential. If you were to hook a speaker to that terminal, if it was like a woofer, it would cause the cone to move and just, you know, be held, and the coil would become very hot, if not be damaged. And of course, that kind of current would flow through the output devices continuously. On this channel, it would get very hot. Now, I did not hook a speaker to it. I did temporarily connect a dummy load or resistive load to the amplifier, and the voltage remained. It didn't change at all, so it appeared to have you know, plenty of current behind it. It wasn't sort of floating and then disappearing when there was a load. Now, the amplifier should have basically no voltage on the speaker terminals. And when I say basically, ideally none, 1 millivolt perhaps, very, very low, maybe in the microvolt range ideally. So basically no voltage on the speaker terminals. The left channel was in fact working that way, but the right channel, again, a negative 12 volts roughly. When the amplifier warmed up, it seemed to go to maybe a negative 7 volts, at times maybe as much as negative 20. It did fluctuate a fair amount, but at no time was it ever correct. I checked the bias, and the bias was not correct, but it wasn't too far off. I think it was about a 12 millivolts on the test points. 10 millivolts is the specified value, so it wasn't too far off, but we could adjust that later. But I didn't see anything wrong with the bias until some additional troubleshooting, and the bias voltage disappeared on this channel, completely shut off. So that, of course, was not a good sign, and that happened, just appeared to be random while I was doing some testing and measurements, and I had a voltmeter connected to the test points on here and over here for the bias, and it suddenly just dropped to 0. Of course, I couldn't cause that to happen again when I poked and I was pushing on some components over here and taking some readings, and then it reappeared again, and then it seemed to come and go kind of randomly. So anytime you have a situation where you have a voltage or a reading like that, it's, you know, all or none, coming and going, you suspect an open or an intermittent connection, oftentimes a cold solder joint or something like that. So I didn't believe that that would be causing the DC offset voltage, but I wasn't sure. It seemed unrelated. It seemed like a separate problem, but I certainly began looking for open connections, cold solder joints, and so on. And it became apparent that this circuit board would need to be removed to do any component replacements and to investigate for any solder connections that might be a problem. So you can see how when the amplifier is disassembled, this module is able to be removed out, and the circuit board is able to be removed and basically positioned so that you can get to the back side. And there's some wires to desolder. There are some very short leads or wires on the input RCA jacks. Incidentally, almost the hardest part to disassemble was the nut on the back side of the RCA jacks. It had basically Loctite on the threads. It was extremely hard to remove those nuts that were on those RCA jacks. I was almost afraid those jacks were going to be destroyed. There's no way to hold on the outside, and I had a pair of pliers with a cloth so that it didn't damage the RCA jack or scratch or score it, as a gold plating on them. And luckily they survived. I figured I could replace them if I had to, but I didn't want to damage them if possible. So that actually was one of the most difficult things to remove, and it would appear to be so simple. But once those were out and the circuit board was able to be taken out, I did not see any solder connections that looked bad on the back side of this board. However, you can see what I did find on one of the transistors on the heatsink. And you can see that there was an open solder, and that's right in the bias circuit, and was causing that on and off condition basically of the bias voltage. So with that transistor soldered in place, the transistor tested fine. There was no issue, but it was just simply one leg or one lead of the transistor was loose, and the solder, probably from thermal stress, had cracked. But it did not take care of the problem with the DC offset voltage. That problem remained. So the one problem was fixed, and the bias voltage was very steady, no issues. So here's the schematic for the right channel. You can see the RCA input jack for the input signal right here. The differential transistor pair right here, constant current source, the VA amp, some of the bias circuitry right here, the transistor that tracks on for the thermal compensation in the bias circuit is not shown, but you can see the collector base emitter leads right here, the VR for the bias circuitry right here. So my initial concern was in this transistor pair, and I felt that changing these may solve the problem. I thought that the DC offset could be related to one of these failing or not responding correctly to the offset voltage from this op amp. Now I did notice that this op amp's offset voltage was very low, 1 volt or even less, and I was not sure if this op amp was a problem or not, but I didn't have that op amp on hand to replace it. That op amp is an LT1006. It was made by Linear Technologies. I didn't have that, so I was not able to change that, but I did have some original Sanyo transistors of the correct original part numbers for these transistors, this constant current source, this switch. So I was able to change several of these transistors, hoping that that would solve the problem. Now, over here, the VA stage, I didn't feel that that would be a problem. I didn't have that transistor, and I didn't think that that would be causing the DC offset. I didn't want to get into a wholesale replacement of many transistors or purchasing transistors that weren't necessary. So I changed the ones that seemed logical that would cause the DC offset, and certainly these two right here in this differential amp could cause that. Now this circuit, these don't need to be matched particularly close because of this op amp. Well, changing those transistors ultimately did not solve the problem. So with those transistors in place, the amplifier had exactly the same DC offset voltage, no change whatsoever. Again, a -12, -17, it would jump around, but it was not correcting the offset whatsoever. And I came back to this op amp and took some readings. Now we do have the same circuit for the left channel up above, and you can see the schematic down. It's just basically the identical circuit. So in doing this troubleshooting, I was taking measurements on the left and right channel, for comparison. And I did notice that the output of the op amp on the right channel was very low. It was about 1 volt, if that. It seemed to vary a little bit, maybe even down to 1/10 of a volt. The op amp on the left channel, again, that left channel was working correctly, was very close to 5 volts. So I thought, well, the op amp is likely to be the next component. I'm running out of components. There's not a lot left. There are some capacitors around here, some resistors, very high value resistors in the megohm range. So I pulled the op amp off the board, checked these capacitors, checked these resistors, everything checked perfectly fine. So I ordered up that op amp. That op amp, again, it's an LT1006, LT1006. ADCOM, they mark it as an ADCOM 3A, but in reality it's an LT1006 by Linear Technologies. It's a single supply op amp, and that solved the problem. So with that new op amp in place, the DC offset voltage fell to basically 0. Now, when I replaced these transistors, I did match them very, very close, and I noticed that the transistors that were removed had a considerable difference in some of the readings. So I didn't feel too bad about replacing those. Some improvement, I suppose, although this circuit, when it's working correctly, can compensate for some differences here. But again, not a bad thing to change those out and get them matched a little bit closer. So back to the circuit board, you can see that op amp is over here. That's the op amp that was changed. A little bit hard to see because the shadows, the transistors are back in this corner here. These transistors were not changed. These are original. There was no need to change those, nothing wrong with them. These capacitors around the op amp tested perfectly fine. Several resistors tested perfectly fine around it, so there was no other indication of troubles in that circuit other than the op amp, and it again did correct the problem. The other capacitors in this amplifier that are electrolytic do not pass any audio signal, but while this board was out, I thought it would be a good time to change those. Again, this amp is at least 30-some years old at this point. So these two capacitors are a power supply for the op amp, and it's approximately 19 volts. It's regulated by a Zener diode. So these two capacitors were changed out, as well as this capacitor and this capacitor. These capacitors are in the bias voltage generator circuit, and again, no audio signal through those, but a good thing to change out. And I will show you a reading on one of these in particular that was not looking very good. So again, felt good about replacing those. Zoom back out a bit here, and you can see in the rest of the caps here, here, and over here, these were changed and upgraded to a slightly larger value of capacitance. The physical size of the capacitor is identical to the originals. The originals, once out of the circuit, they tested reasonably well, but the new capacitors tested slightly better, particularly on the ESR. The ESR on these tested considerably better on the replacements. Also increased the voltage rating on these replacements, 35 volts instead of 25 volts. Again, on a 19-volt circuit, I like to see a little bit higher than a 25-volt rated cap. And also the caps on the bias generator, I increased the value on these, a bit higher voltage, never changing the capacitance value on these or these. That value microfarad rating is fine, but increasing the voltage on those. These have a slightly higher voltage rating as well as a slightly higher capacitance. These are filter caps. They put them on these boards because these are the power supply rail, and these wires have some length off of the main filter caps, and it adds a bit of capacitance out here for transients and surges that would be needed when it processes an audio signal, and just some filtering on the ends of these wires that are out here. So you can also see those wires are twisted to prevent any hum or other problems, which is good practice to do. So I will show you the capacitor that tested not faulty, but it didn't test very well on the ESR meter, so we'll take a look at that, and you can see the other components that were taken out as well. Okay, here are the components that were taken out and replaced. You can see we have the filter capacitors that were on those output boards with the output devices, the capacitors that are on those 19-volt power supplies, the bias speed-up capacitors, and here's the little op amp and the 4 transistors. 2 of them are the differential pair, and the other 2 were one was a constant current source, and one was basically a switch. So these 2 small capacitors in particular, of all the capacitors, tested very poor. They're technically in spec, but when you compare to a new capacitor, I don't feel bad about changing them at all, because they do test considerably worse than the brand new component. So we'll take a reading on this capacitor. You can see it's analyzing. So we have 4.56 microfarad, well within spec on the capacitance, with that ESR of 15.4 ohms, 15.4 ohms. So that's quite high. Again, if you look up on a chart for allowable ESR for this capacitor, that is within what would be considered okay, but we'll take a look at what a new component reads, and you'll see it's not looking too good. This one, 14.4, so again, quite high, but the capacitance does read, correct for what the capacitor is actually rated 4.7, so perfectly fine on the capacitance. Here is one of the new capacitors, same as what was installed on the circuit board, and we see on one of these We have 0.61 ohms ESR. Good capacitance reading as well, 4.6, but again, ESR of 0.61 compared to those other readings that were much, much higher. So certainly a good thing to change those capacitors out. Some of these other capacitors, if we take a look on these, the readings were not terrible. You know, they were okay considering their age, but you know, 0.53 ohms ESR, 48 microfarad, and I think these were 105 for the temperature, so they were well rated. 160 volt, 47 microfarads. So I did test all of them, and I didn't see anything that was too obviously wrong on any of the others, but those two were not looking too good. So, and they would only get worse with age. The capacitors would never improve. So good to get those changed out, particularly when the board is out, and it's not terrible to remove the board, but you have to unsolder some things, and it's the time to do it. So always good. Now, the main filter caps in the amplifier tested absolutely fine. Their ESR reads very, very good. They have no issues whatsoever. The capacitance value is very close on all of them, so those filter caps are looking fine, and see no reason to change those. There's a fair amount of heat on these capacitors just because they're so close to the output devices. They do get quite warm in there, so again, not a bad thing to change after 30 years of time. So in troubleshooting, the decision to take a look and ultimately replace the components over here related to the differential amplifier and some of those small signal transistors on this board, rather than even remove or test any of the output devices, was because that output DC offset voltage was -7 or -10 volts. It varied a bit. Sometimes it may be as much as -20, but often close to -10 volts, -12 in that range. It did seem a bit temperature related. As the amp warmed up, it dropped somewhat. The output transistors, their collector is tied to the power supply rail. So one group is on the negative rail, one group on the positive rail. If a group on the negative rail had a shorted transistor, you would see the full rail voltage appear at the speaker terminals. In this amplifier, that rail voltage is 82 volts on the positive rail, 82 volts on the negative rail. So if you had a shorted output device, you would see 82 volts on the speaker terminals, and of course, you know, that wasn't the case. So I was immediately looking at something other than those output devices. Now, if nothing had solved the problem on this board, we would have to start looking at these devices or something over here perhaps. But initially, those were not a concern, and ultimately ended up not being any problem whatsoever. So now that the amplifier has the components replaced, the op amp, the transistors, and several new capacitors, let's take a look at some measurements on the amplifier and verify that it is in fact operating correctly. The amplifier has been powered up now for over an hour, and I have this DC voltmeter monitoring the right channel output at the speaker terminals. You can see that the output is holding generally under 1 millivolt down in the microvolt range most of the time, so well within spec. It's looking very good. The voltmeter is set on the 1 volt scale, so this is 1 millivolt when that ticks up to a 1, but generally down in the microvolt range. So the final step will be to adjust and check the DC bias voltage on the output stage. Okay, we're ready to take the DC bias voltage reading. The DC bias voltage reading is taken across test points here and here for the right channel, here and here for the left channel. The adjustment is this VR here and over here. Before you take the DC bias reading, you want to make sure that there is no input signal, so the RCA jacks are left disconnected, and the speaker terminal jacks are also disconnected. There is no load connected to the amplifier. Now the specified value is 10 millivolts plus minus 1 millivolt. So we'll take a reading across these test points over here. We see 9.9 millivolts, so that looks very good. Now the reading is a negative 9.9. If you were to flip the test leads around the other way, you'll just get the positive reading. So it does not matter which way the probes are attached. It will create the same reading. So on the left channel we see 9.7 millivolts, so well within spec. So it's looking very good. Now initially the bias voltage was reading too high, and I did bring those down, the adjustments down a bit. They probably were bumped during the repairs that were done. That board was of course taken in and out several times. And you don't want to power up the amplifier and ignore the bias reading initially if it's too high. Of course the output stage would run very warm, if not hot. You don't want to cause any damage. So I did monitor that as the amplifier warmed up. It settled in nicely and is well within spec. So no adjustments at this point. The final, or no further adjustments at this point. The final bias voltage reading will be taken after the amplifier has run under a load. So you want to make sure that the amplifier warms up and then is able to stabilize, and that the bias voltage reading remains within spec. It will change when the amplifier is hot, and of course when the amplifier is cold and is first turned on, but it should stabilize and come back to very close to the readings that we just saw. The test given in the service manual is to operate the amplifier with an 8 ohm load, 66 watts. With Ohm's law we can figure out that that is a 22.98 volt signal that would come out of the amplifier. So 22.98 volts across the 8 ohms will give us 66 watts. So we'll look for that signal on the oscilloscope, and we'll run the load test. And the load test is done for 10 minutes with the cover on. The amplifier is operating into an 8 ohm load. I have two 4 ohm resistors connected in series. Each resistor is rated 300 watts. The signal generator on the right is generating a 1 kilohertz sine wave at 995 millivolts RMS. And you can see on the oscilloscope the output is measured across the speaker terminals or across the load, and it verifies we have our 22.98 volts RMS, which gives us our 66 watts across the 8 ohm load. The waveform looks very good. You can see the positive peaks and the negative peaks are the same number of gradicules above and below ground reference, which is in the middle. If there was a DC offset, this waveform would shift above or below ground depending on the polarity of the offset. Again, this is the channel that had that DC offset problem. So the waveform again is looking very good. I'll repeat the test on the left channel to verify that it's operating correctly and that the bias is set correctly. And I'll also do a full power test. The amplifier is rated 200 watts. We'll want to make sure that it's able to do that and not show any clipping on the waveform or any other problems. Also, I'm going to test to make sure that the gain on the left and right channels is equal, and I'll show you how to do that in just a moment. This is the left channel operating into an 8 ohm load. Again, we have a 1 kilohertz sine wave input to the amplifier, and the amplifier is generating 66 watts into the 8 ohm load. The amplifier is now disconnected from a load. There is no connection made to either the left or right channel, no input signal. The speaker terminals are disconnected. The right channel was the channel I tested first under load. It's had some time now to cool and for the temperature to equalize. So we'll take a measurement for its bias. And we see 10.8 millivolts. So that looks very good. There's no further adjustment needed on that channel. On the left channel, this channel's still quite warm. I just disconnected the load. We see 14.4 millivolts. So that channel needs to cool a little bit longer. You can feel that heatsink is noticeably warmer than the right channel. So we'll let that cool a little bit longer and take another reading. If it still reads high, it may need an adjustment, but we'll let things equalize a bit before we make any further adjustments. So we'll check the left channel again. It's been several minutes since the load was disconnected. And 10.7 millivolts, so we're right within specification, no issues at all. And again, on the right channel, this has been sitting idle now for a while, right at 10 millivolts, so exactly within specification. So the bias adjustment is complete. Everything is looking very good at this point. So we want to verify that the left and right channels have equal gain on the amplifier. An easy way to do that is to use the oscilloscope and feed an identical signal to both channels. So we can see we're doing that with that Y adapter on the signal generator, 1 kilohertz sine wave. And on the oscilloscope, channel 1 is the right channel, channel 2 is the left channel. The volts per division is set the same, 2 volts per division. If I move channel 2 up to channel 1 so that the traces overlay, like so, you can see it completely disappears, which verifies that both outputs of the amplifier are in fact identical. If one was slightly higher or lower, you would not be able to overlay them. You would see perhaps a bit more above or below in the trough of the sine wave or in the peak of the sine wave. So again, come down like so, back up. It completely blends into what appears to be one signal, one waveform. So it shows that the outputs are in fact identical, and it's looking very good. So here we have a full power output test, 40 volts RMS output, which is 200 watts into an 8 ohm load, 1.73 volts RMS input, 1 kilohertz, and that's on the right channel. And here's the left channel full power output test, 200 watts, no problems, 40 volts output at across 8 ohms, 1.73 volts RMS input, 1 kilohertz. The repairs on the ADCOM GFA-555 Mark II power amplifier are complete. The repairs were successful in addressing all the issues that the amplifier was having. The amplifier is performing very well. If you enjoyed this video, please give us a thumbs up, and until next time, goodbye.